Okay, the topic of this chapter is instance-based learning. The basic idea of instance-based learning is that suppose you have new data and you want to classify the new data, then you find some data similar to the new data. Okay, and then based on the target values of the similar data, you make decision. Okay, so that's a basic idea of instance-based learning. So algorithm is quite straightforward and simple. So let's take a look at this example here. Let's say we have a new animal and you want to classify this animal, whether it is a goose or a chicken or duck or swan or chick. Okay, then let's say this animal is very similar to this duck. Okay, then in that case we conclude that this new animal is duck. Okay, so that's how it works. It works in instance-based learning. So find something similar, and based on the value of the similar data, you classify new data. Okay, that's the basic idea of instance-based learning. So as I said, our basic idea is if the new data it works like a duck and quacks like a duck, then probably it is a duck. So that's basic idea. So in this example here, we have minus data and plus data here. And let's say we have new data in red here. Okay, and you want to classify whether this new data is plus or minus, right? So if you use instance-based learning, you find something similar. Okay, so you find your neighbor. So neighbor means similar data. Okay, so for this particular new data, we have a neighbor like this. Let's say these three are neighbors, similar data, and all these neighbors has plus value, right? So we can we can conclude that this data is plus value. Okay, so that's how it works in instance-based learning. So as I said, this instance-based learning is based on the concept of similarity. So we find similar data. So that means this instance-based learning is based on the concept of similarity. Okay. And because of that, this algorithm, instance-based learning, is sometimes called K nearest neighbor. So these are actually same, okay, instance-based learning, IBL, or K nearest neighbor, KNN, are basically the same algorithm. So in this example, let's say X is the new data and you want to classify this X data. And if you choose one neighbor means the most similar data. So in this case, you choose one neighbor minus here. Then based on this is minus, but you have only one neighbor and its target value is minus, then we say this X is minus. In this case, if you choose two neighbor, okay, then we have we have minus and plus, right? So in this case, then the target value for X is depending on the way you combine the value of neighbors, okay? If these neighbors has same weight, same importance, we have a tie. But if you have different weight for each neighbor, then we conclude that this is minus because minus is more close. Okay, minus close to X than plus does, right? So in this case, we use if you give different weight to each neighbor, we say this X is minus. Okay, you're gonna talk about this later on. Okay, So in this case, if you choose 3 neighbor, then we have 1 to 3 neighbor, okay, and in this case, you have a 2 plus and 1 minus. So if you simply choose the majority, then we can conclude x is plus. But again, if you give different weight, different importance to each neighbor, then it's a little unclear, okay, because this one has the highest weight, okay, this one has the highest weight value, importance value. So it is not clear whether it can be plus or minus, okay. Anyway, we're gonna talk about this issue later on in this chapter. So because instance-based learning is based on the concept of similarity, and also it also depends on, as I said here, it depends on the way you combine neighbors, the value of neighbors. Okay, so there are two important operations, two important functions in instance-based learning. The first one is distance functions. How do you define distance or similarity, okay, between two data? Okay, that's the first important issue. And the second important issue is combination function. So select a few neighbors. Then how do you combine them? Okay. So for example, here you select 3 neighbors, right? Then maybe you can give same weight to each neighbor, or you can give different weight to each neighbor. Okay, so depending on your method, you're gonna have different result, right? So anyway, the way you combine this neighbor is important. Okay, that's the issue of combination function. So in this chapter, we're gonna talk about these distance functions and combination functions. The instance-based learning is quite different from other classification learning method, such as decision tree or neural net. In a decision tree or neural net, when the algorithm read training data, it constructs a model, okay, machine learning model. In decision tree case, it constructs a tree, okay, and in neural net case, it constructs a network, right? And then after that, by using this model, by using this model, we classify new data, okay, that's how it works. But in instance-based learning, uh, when the algorithm read training data, it does nothing, okay? It does nothing, okay? And then after that, when it read test data, now all of a sudden this algorithm is super busy, and it now read the entire training data to find similar data of new data, okay? And then you select a few similar data, and based on the class value, target value of that similar data, you make a decision, okay? So that's how it works. So because of this reason, this instance-based learning is sometimes called lazy learners. It is lazy, okay, because when it read training data, it does nothing, okay, and then when it has new data, then now it's very busy and read entire training data, okay, over and over, okay. So that's why this is called lazy learners. So it's like college students. You have homework, and it doesn't start homework, up until the last night of deadline, okay. So it's like lazy learners. So that's difference. So unlike eager learners, okay, other classification algorithms such as decision tree or neural net, it doesn't build the model explicitly, okay. So and then classifying unknown new data is relatively expensive, because when it has a new data, unknown data, now it has to read entire training data. Okay, for each new data, it should read entire training data. Okay, so if you have tons of training data, the algorithm is very slow in testing time. Okay. So strengths of instance-based learning is you can use data as is because you do not build any machine learning model. Okay, you simply store entire training data. So you can use data as is. Okay, and another strength is algorithm is very simple. Okay, it's simply read entire data and find some similar data, some neighbors. Okay, algorithm is very simple. And there is no training, as I said. There is no training. It's you simply read training data and store them. Okay, so there is no training actually. Problems of instance-based learning is it has to store entire or large amount of training data. Okay, it has to store entire training data because later on when it has test data, it has to read the entire training data to find the neighbors, right? So it has to store a large amount of training data. And also the classifying, okay, when you classify test data, this is very slow, very time consuming, okay. And another drawback is, I mentioned this in previous slide, there are two main issues in instance-based learning is distance function and the combination function. So sometimes these are a little tricky to find the optimal distance function or combination function. Okay, so that these are strengths and drawbacks of instance-based learning. This diagram is called a Voronoi diagram, and this one shows the result of one nearest neighbor. Okay, so what it means here is, so these blue dot represent data, okay, training data. And this region means if a new data falls in this area, okay, then its class value is same as this one. For this one, let's say, to this area, if a new data falls in this area, then that class value is same as the class value of this one. Okay, so this diagram is called a Voronoi diagram, and you can draw this diagram when the nearest number of neighbor is 1. Okay, so then you can draw a Voronoi diagram like this. I'm going to explain the mechanism of instance-based learning by using an example here. The goal of this example is to estimate the cost of renting an apartment in the target town called Tuxedo in the New York State by combining data in other towns. So as we know, in instance-based learning, we first find similar data, similar neighbors, okay? And then based on the value of neighbors, we make a decision, right? So if you look at this picture here, we use two variables. The first one is mean home value of city, and the second one is the population of city. So by using these two variables, we can display many cities here, okay? So each dot here represents a city. And the target city, Tuxedo, is here, okay? And then suppose we choose two neighbors, okay? Then we have two neighbors here, which is Shelter Island, and the second one is North Salem. So these two are the neighbors of Tuxedo City. So now we have chosen two neighbors. Then based on using these two neighbors, we're gonna make a decision about this Tuxedo City. Okay. By the way, when I say neighbor here, this neighbor has nothing to do with geographical, physical neighbor. Okay. So these are neighbors in terms of this variable, in terms of this mean home value and their population. Okay, this has nothing to do with actual physical distance in the map. Okay, so we choose to neighbor, and based on neighbor, we're gonna make a decision. Before I move on, I'm gonna talk about these log populations. So for this one, we use original values. Okay, for this population value, we use log population. We put log of population. The reason is population actually follows is a power distribution. Okay, so in it is not Gaussian distribution. It follows Gaussian power distribution. In power distribution, the shape of power distribution looks like this. Okay, it looks like this. Okay, so that means almost every data lies here. Okay, and then there are just a few data here, 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 something like that. Okay, it looks something like this. Okay, so let's say vast majority, like maybe 90% or something, 90% of city lies here, very compact here, and then just a few, like I don't know, maybe New York, LA, or Chicago or something. Okay, so that's what's happening. If you do not use log, that's what's gonna happen. Okay, so by using log here, now the data is kind of spread kind of evenly along the x-axis. Okay, that's why we put log here. So we have chosen two neighbors, okay, Shelter Island and North Salem. And this shows the detailed information of these neighbors. So Shelter Island, this is population, this is the median rent value, and this is the distribution of rent values. And for North Salem, this is population, this is median rent value, and this shows the distribution of rent values. So now the question is, how do you combine this information from the neighbors to estimate the rent value in Tuxedo City? Okay, that's the question. So if you look here, even though the median rent is pretty close, okay, but the distribution of rent is quite different actually. In Shelter Island, the most frequent rent range is this area here, okay, but in North Salem, the most frequent rent range is this one. So even though the median rent is close, pretty close, but their distribution is quite different. Okay, so how do you combine this value and come up with a new estimate value in Tuxedo City? Okay, we have chosen two neighbors, and also we have seen the data of these neighbors. Now let's combine these two data and come up with the estimate of rent in Tuxedo City. The first method you can think of is we use the median rent of the neighbor cities, okay, which is 804 and 1,150. So we compute the average of these two, which is 977. Okay, we can use this one for the estimate of rent in Tuxedo. So the actual median rent in Tuxedo is 907, so pretty close, okay. Second method we can think of is if you look at the distribution of the rent, okay, and then in the distribution of rent, we choose the most common rent, okay, we choose the most common rent and use those most common rents as our estimate, okay. So we average the most common rent of these neighbors. The second method. So the midpoint of the most common range, okay, in Shelter Island is 1,000. And for North Salem, the midpoint of the most common range is 1,250. So by computing the average between these two, our estimate is 1,125. Okay. So the actual, the most common rent in Tuxedo is between 1,000 and 1,500. So the midpoint is 1,250. So this is our estimate, and this is the actual midpoint of most common rent. Okay, so pretty close. So in method 1, this is our estimate, this is actual value. It slightly overestimate, okay, the real value, real median rent. In method 2, this is our method, and it slightly underestimate the most common rent value in Tuxedo, okay? So depending on which method, you can come up with a different estimate, okay? It's hard to tell which method is better, okay, than the other, okay? It all depends on your data and your application. And earlier in this chapter, I said there are two important issues in the instance-based learning. The first one is how to define a distance function, okay, and the second issue is how to combine the values of neighbors. So this one here explains the distance functions in instance-based learning. So the distance function we're going to use in instance-based learning has some properties such as well-defined identity, commutativity, and triangle inequality. Okay, and well-defined is the distance between data A and B should be non-negative. Okay, so this property is called well-defined. You don't have a negative distance. Okay, and identity means distance between same data is 0. Okay, and the commutativity is distance between A and B is same as distance between B and A. Okay, that's called commutativity. And triangle inequality is distance between A and B is actually greater than or equal to the distance between A and C plus distance between C and B. Okay, if you draw a triangle, this is clear. Okay, so if you define a distance function in instance-based learning, you make sure these properties are satisfied. Okay. One thing interesting in distance function is, so suppose you choose a nearest neighbor, okay, of record B, okay, and it turns out to be A. So A is the nearest neighbor of record B, okay. So A is the nearest neighbor of record B, okay. But that doesn't necessarily mean A is the nearest neighbor of B. So the other direction is not always is true. Okay. So A may be the nearest neighbor of B, but the other way doesn't always be true. Okay. So A may not be the nearest neighbor of B. Okay. If you look at this picture here, A is the nearest neighbor of B. Okay, but B is not the nearest neighbor of A. Okay. Okay, now let's build a distance function. When you build a distance function between two data, actually you compute the distance for every attribute first, and then this attribute distance will be combined later. Okay, that's how we compute the distance of data in IBL. So let's take a look at this example here. This one has 5 data and it has 3 attributes, gender, age, and salary. Gender attribute is categorical, okay, and age salary is the numeric attribute. So it has 2 numeric attribute and 1 categorical attribute, okay. And I said we compute the distance for each attribute first, okay? So, but the way we compute the distance in attribute actually depends on the format of attribute, okay? So if the attribute is numeric attribute, we use this method here, one of this method here, and its attribute is categorical. We're going to use a method in the next slide, okay? By the way, this picture shows, so if this picture data is displayed in this 3D coordinate here, okay? So anyway, let's compute the distance for each attribute, okay? If the attribute is numeric, then we use one of these 4 methods. These 4 are the most popular distance functions for numeric attribute. The first one is absolute value of difference. So the absolute value of A minus B. So A, B here is the attribute values, okay? Second method is square of the difference, which is A minus B squared. And the third one is normalized absolute value. So this is the absolute value divided by maximum difference. Actually, this is the absolute value divided by the range of attribute. Okay, maximum difference is the range of the attribute. The fourth method is the absolute value divided by a standard deviation. Okay, divided by instead of maximum difference, it's divided by standard deviation. Okay, so these are the most common distance functions for numeric attribute. So if your attribute is numeric like age or salary, okay, then when you compute the distance between 2 attribute values, you can use one of these, okay? This table shows the example of computing attribute distance for numeric attribute. So for example, the age is a numeric attribute, and in previous slide, age has 5 different values here, okay? So for each pair of values, we compute the distance here, okay? So in this case, we use normalized absolute value. So absolute value is divided by the range of attribute, okay? So this is how we compute. This is the result of the distance using normalized absolute value for attribute age. Okay. So we have seen how we compute the distance for a numeric attribute. Okay. The second attribute type is categorical attribute. So for categorical attribute, actually this is very simple. We use identical function. Okay. So distance between female is the same, right? Distance is 0. And if distance between male is 1. So this is identical function. So if the value is same, distance is 0, value is different, distance is 1. Okay, so it's very simple. It's identity function. We're going to use identity function to compute the distance in categorical attribute. Okay, but actually in real instance-based learning, we have more advanced distance definition, distance function for categorical attribute. But for now, we're gonna stick with the identical function for computing distance in categorical attribute. Okay. So now we have computed the distance for each attribute. Okay, whether it is a numeric attribute or a categorical attribute. Okay, now it is time to combine them. Okay, for each attribute, now we have its distance, right? Now we combine them. The way we combine them, actually, we have 4 choices here. The first choice is called the Manhattan distance. This one is very simple. So this is the distance in gender attribute. This is distance in age attribute. This is distance in salary attribute. Simply add them together, okay? And then this one is the final distance between attribute data A and data B, okay? Then it's called the Manhattan distance. Second one is normalized summation or normalized Manhattan. So the second method is this Manhattan distance is divided by maximum, okay, of this value. So normalized version. And Euclidean distance is this attribute distance, okay, gender is squared, and this age distance is squared, and this salary distance is squared, and altogether these are you put square root here, and this is Euclidean distance between data A and B. Okay, this is the formula, very formula Euclidean distance. You plot 2 data in a coordinate space, then you can easily compute Euclidean distance between these 2 data points, right? This is exactly same, okay? And the last one is cosine similarity, and we're gonna talk about this a little later. Okay, so anyway, you compute the distance for every attribute, okay? And then using one of this method, you combine them, okay? So that's how it works when you compute distance functions for 2 data, okay? We have learned how to compute attribute distance depending on attribute type. And also we learned how to combine them to compute the record distance. So in this table, for each record, we compute the nearest neighbors by using different record distance functions. So for example, for record 1, if you use dsum, which is Manhattan distance, then the nearest neighbors are 1, 4, 5 to 3. And for record 2, if you use, let's say, dnorm, which is normalized Manhattan distance, then the nearest neighbors are 2, 5, 3, 4, 1. Okay. By the way, this 2 is the nearest neighbor and the 1 is the most distant neighbor. One thing is interesting here is in this particular case, regardless of this record distance function, we have same result, right? So, but this is a kind of coincidence, okay? This is not always true. So in many other cases, depending on this record distance function, you're going to have different result. So let's take a look at another example here. Let's say we have a new record like this, whose gender is female, age is 45, and the salary is 100,000. Okay, then we compute the distance between this data and each of this record. Okay, then when you use this sum, which is Manhattan distance, then the distance between this and record 1 is this 1.662. Then the distance between this and record 2 using Manhattan distance is 1.659, etc. Okay. So after computing all this distance, these are neighbors of this new data. Okay, so the neighbors of this data is 4, 3, 5, 2, 1. So in a similar way, if you compute the distance between these and each of these by using the norm, normalized Manhattan, these are the result, these are the distance, okay? So by looking at this number, the neighbors are 4, 3, 5, 2, 1. And finally, if you use Euclidean distance, okay, and compute distance between these and each of these by using Euclidean distance, these are the result. And now the nearest neighbors are 4, 1, 5, 2, 3. So as you can see here, in most cases, depending on the record distance function, we have different nearest neighbors. Okay, as you can see here, this sum and the norm have same nearest neighbors, but the Euclidean distance has different nearest neighbor. Okay. So by using these neighbors, you can now make decisions based on these neighbors. So you can choose, let's say, one neighbor or two neighbors or three neighbors, okay, whatever. And then based on these neighbors, now you can make decisions, okay? Final issue here is the combination function can also incorporate weights, okay? What it means here is, let's say in this data, we have three attributes, gender, age, and salary, okay? Then let's suppose with respect to the target value, okay, then we know that this salary attribute is much more important than, let's say, gender, okay? Then we are able to give a different weight to each attribute. Okay, so if you know that this attribute is much more important than this attribute with respect to the target value, then you may give a high weight value to this attribute and you may give a low weight value to this attribute. Okay, that's what it says here. So when you use a combination function, you can give weight to each attribute. Okay, so this is called a feature weighting. Okay, and this is a method to incorporate prior knowledge into this IVL algorithm. Okay. This slide shows the detailed derivation process of computing distance between new data and each of the record. In this case, we assume we use a normalized absolute value to compute the numeric attribute, and we use Manhattan distance for a record distance function. Okay, so by using these two, we're going to compute the distance between new data in previous slide. Actually, it's given here. and each of these records. Okay. So let's take a look at the first one. Okay, for example, so distance between 1 and new. This is record 1 and new. The distance between these two is, first you compute distance between distance of gender attribute. Okay, so distance between female and female, these are the same value, right? Distance between female. And then you compute distance between 27 and 45 in age attribute. Okay, and then you compute distance between this salary and this salary right here. Okay, so this is identity function, so this is 0, the values are same, that means this distance is 0. And for this one we use normalized absolute value, which is this. Difference is divided by maximum range. Okay, in this case maximum is 52. Okay, minimum is 27, so this is maximum range. Again, for this we use normalized absolute value, so difference divided by maximum range. So by computing this, we have 1.66. Okay, so by using normalized absolute value and Manhattan distance, the distance between record 1 and the new is 1.66. So in a similar way, you can compute the distance between record 2 and the new, record 3 and new, record 4 and new, record 5 and new. Okay, these results are given in previous slide. Also, it is given in the next slide. Okay. After computing the distance between new data, you want to classify, and then with each of the record, then you select some neighbors, right? And then the next step is how to combine the results of nearest neighbors you have selected. Okay, that's the main topic in this slide. Okay. So actually, there are two methods to combine the results of nearest neighbors. So the first one is majority voting, and the second one is weighted voting. So in majority voting, each neighbor has one vote. Okay, it's kind of a democracy system. And the second method is each neighbor has different weight. Okay, it's like a shareholder in a company. Okay, so we have a two method, and usually it is known that this weighted voting shows better performance than this majority voting. So IBL uses this voting system, whether it can be majority voting or weighted voting. So when the task is to assign a single class, after voting, you simply select the one with the most vote. Okay. So usually the k is the number of neighbors you're gonna choose. Okay. So this k, value of k, should be odd number, like 3, 5, 7 or something. Okay, to avoid the tie break. If k is even number, and if you use majority voting, sometimes we have a tie. Okay, so to avoid that, usually this k value is odd number. Usually it's like a 7 or 9 or something. Okay. When there are C category values, C class values, you have at least C plus 1 neighbors to make sure that at least one class has multiple vote. Okay, so that's kind of a small tip to choose a k value. The first method for combining the results of nearest neighbor is majority voting. So you're going to take a look at the example of majority voting here. And this table shows the result of distance between new data and each record. So For example, the distance between record 1 and the new is 1.66. This one here is the class label for record 1. This is class label for record 2. Okay. So by using this table, we are able to compute the nearest neighbors. Okay. So when you choose this neighbor, you choose the smallest distance. Okay. Smallest distance means the nearest neighbor. Okay. So 4 is the nearest neighbor. Second nearest neighbor is this one. Okay. So 3 is next neighbor, etc. So our nearest neighbor is 4, 3, 5, 2, 1. And their corresponding class values are yy and yn. Okay. So k is number of neighbor you're going to choose. So if you k equal 1 means you choose one neighbor, then you choose the first neighbor, which is 4 here. Okay, so you choose 4, only one neighbor, and the class value of 4 is y. Okay, so your prediction is y. If you choose two neighbors, that means you choose these two, and their corresponding class values are y, y. Okay, so everything is y. Your prediction is y. And if k is 3, that means you choose 3 neighbors. So you choose 3, 4, 3, 5. Okay, and their corresponding class values are y, y, n. So majority voting with the class value with the most vote wins. So we have 2y and 1n. Okay, so y is winner. So your prediction is y. The same thing, if k is 5, you choose all of them, and we have 3y, 2n, so y is the winner. Okay. If you use Euclidean distance, then the neighbors will be like this. Okay, and their corresponding class values are like this. So if you choose one neighbor, which is 4, then your class value is y. If you choose two neighbors, you're going to choose 4, 1, and their class values will be y, n. Okay, 1, y, 1, n. So we have a tie. Okay, in majority voting, each data has same vote, 1 vote. So in this case, we choose two neighbors, and their class values are y, n. So we have tie, 1, y, y, n, 1, n. So this question mark means we cannot decide. So if you choose 3 neighbors, y, n, n, so n is majority, so n is the answer. K is 4, again we have y, n, and y, 2y, 2n, so you cannot decide. If k is 5, you have 3y, 2n, so y is majority. Okay, so that's how it works in majority voting. So each neighbor has 1 vote. Okay, and the class value with the most vote wins. Okay. Sometimes you can compute the confidence of your predictions. Okay, so let's take a look at this example here. Suppose you use Manhattan distance, this sum, and the k equals 3, which is this, right? So in this case, you choose 3 neighbor. Okay, 4, 3, 5, and their class values are y, y, n, right? So you have 2y and 1n. Okay. Confidence is defined as the class value, the vote of class value. Okay, the vote of your prediction divided by total vote. So in this case, your prediction is y. Okay, so vote of y is 2. Okay, divided by total vote. Total vote is 3, right? So 2 divided by 3 is 67%. Okay, that's how you compute this confidence. One more example here is, let's say k is 5. You select 5 neighbors. Okay, everything here. So there are 3y, 2n. Okay, so your prediction is y. Okay, so your vote of number of vote for this prediction is 3, okay, 3y, and total vote is 5. So 3 divided by 5 is 60%. Okay, that's how you compute confidence in majority voting. The second method for combining the result of a nearest neighbor is weighted voting. Unlike majority voting, in weighted voting, each neighbor now has a different weight or a different importance or different voting power. So we can say all neighbors are not created equal. So it is more like a shareholder in a company. So I said each neighbor now has different weight. So now we have to compute the weight of each neighbor. Okay. There are many methods of computing the weight values of each neighbor. In this example, you're gonna compute the weight as the inverse value of distance, which is defined here. Okay. So in this example, the weight is 1 over distance. Okay. Yeah, of course, you can use some other method of computing weight, but in this example, you're going to use this formula. So by using this definition, we can now you compute the weight of each data. So in this case, the distance between data 1 and the new is this 1.66. So the weight is the inverse value, which is 0.602. For this one, for record 2, now using the same way, the weight is now 0.606. So this the weight of data 3 is this, the weight of 4 is this, weight of 5 is this. Okay, and these are the class values for each record. Okay, using this now we can do weight voting. Okay, suppose you choose one neighbor, okay, then you choose the most nearest neighbor, which is this. This data for record 4 has highest weight, right? So you choose this one, okay, and here this is the summation of y weight, and this one here is the summation of no weight, okay? So you choose one, you choose the one nearest neighbor, k equals 1, you choose this one because this one has highest weight value, okay? And its class value is y. So that's why we have 1 to 0. So 1 is the summation of y weight. This is summation of no weight, okay, n weight, okay? And if you choose, let's say, this one, k equals 4, then you choose 4 nearest neighbor. Then you choose this one, okay, and this is second highest weight, and the third highest weight is this, and the fourth highest weight is this. So basically you choose this 4, okay. So you choose this 4, and we have 3y and 1n, right? So you do the summation of these 3, which is given here, right? 1 plus this is here, and then this one, okay, the weight of n value comes here. So that's how we compute okay, the summation of weight here. So let's say it's weighted in weighted voting, you compare the summation of weight here, okay? So whichever is greater, whichever is bigger is the final decision, okay? So in this case, this is bigger than this. That means our prediction is yes, okay? So in this case, you compare these two, and this is bigger than this, right? So our prediction is again y, okay? Yes. Same thing. So you compare the weight, the summation of the weight here, these two, and choose whatever is bigger. Okay, so that's how it works in weighted voting. We can also compute the confidence level in weighted voting. So the confidence level is defined as the ratio of winning weights over the total weight. So the definition is here. The confidence of prediction is the sum of winning weight divided by sum of total weight. So let's take a look at example. So in this case, k equals 4. We choose 4 neighbors, these 4, okay? And 3 of them are yes, and 1 of them is no, right? So the confidence is the sum of winning weight. In this case, winning weight, winning value is y, right? So summation of y, which is this, okay, it comes here. Summation of y weight is here, and then it is divided by the entire weight, okay? So the summation of all weight comes here, okay? So you compute this, it is now 0.66, okay? So for this particular case, okay, the confidence is 66%, okay? That's how we compute confidence level. And finally, if you use weighted voting, it actually eliminates the ambiguous results for even numbers. If you remember in majority voting, if you choose even number of neighbors, okay, and then sometimes you have tie in the number of number of the class values, okay. So, but in weighted voting, you don't have to worry about it because every weight value is not integer anymore. It is a real number, okay. So definitely you have a winner, okay. So that's one advantage of using weighted voting. So this slide is about the Minkowski distance, also known as p-norm. Earlier, when we compute the attribute distance, we have seen Manhattan distance and Euclidean distance. And actually, these distances are a special case of this Minkowski distance. Okay, so this is the definition of Minkowski distance. So distance between xi and xj is the following. So you compute the xi1 minus xj1. Here xi1 means the first attribute of data xi, and this one is the first attribute of data xj. So you compute the difference, absolute value of difference, and to the power of q, and you do summation, and you do q square root. So that's the definition of Minkowski distance between these two data. So as you can see, if q value is 2, then this distance becomes Euclidean distance, okay? And also if q value is 1, and this distance becomes a Manhattan distance, okay? So as you can see, this distance is Euclidean or Manhattan distance is a special case of Minkowski distance. By the way, we call Euclidean distance L2 norm and Manhattan distance L1 norm. In other cases, when q equals 0, this distance is called a Hamming distance. This is simply the number of different attribute values, okay? That's a Hamming distance. This happens when q equals 0. If q value goes infinity, then this distance means it's the maximum difference between attribute values, okay? And that's the definition of Minkowski distance when q becomes infinite, okay? And in other cases, if q goes negative infinity, and this is just the minimum difference values in attribute differences, okay? So this is the Minkowski distance when Q goes negative infinity. By the way, if Q goes infinity, this is called the Chebyshev distance, and also you can call it L maximum. And also, if Q goes negative infinity, it's you can call it L minimum. Okay. So anyway, this Minkowski distance is a generalization of many different distance measures. Near the beginning of this chapter, I said the distance function we're going to use in IBL is supposed to satisfy these properties. So Minkowski distance actually satisfies each of these conditions. So that means we are able to use this Minkowski distance in IBL method. The next similarity measure we're going to study is cosine similarity. And actually the similarity is the opposite of distance. So in IBL you can use either of them. So what is cosine similarity and why do we need it? Let's begin with this example. So here x-axis is tail, size of tail, and the y-axis is the body part ratio. Okay, and we have 4 data, and let's assume each data is represented as a vector. Okay, so this is a vector of big fish, little fish vector, big cat vector, and the little cat vector. Okay. So in this case, if you compute the nearest neighbor of little cat, okay, then the nearest neighbor of little cat is little fish, because the distance here, okay, is smaller than the distance here, right? So the little fish is the nearest neighbor of little cat, okay. But this conclusion is weird, okay. So in our nature, okay, big cat is more similar to little cat, okay, than the little fish is, right? So if you use traditional Euclidean or Manhattan distance, we have a very strange conclusion saying little fish is more similar to little cat than big cat, right? So to solve this problem, we use another measure called cosine similarity. So in cosine similarity, the definition is, so when you measure the distance between two data, okay, we actually compute the angle between these two vectors. So suppose you compute this similarity between these two data, okay? Instead of computing Euclidean distance or Manhattan distance like this, you compute the angle between these two vectors. In this case, this one, okay? That is cosine similarity. So if you compute the similarity between these two data, big fish, little fish, then in cosine similarity, you compute the angle between these two vectors. If you compute similarity between little fish and big cat, then the similarity is this one. Okay, so that's how it works in cosine similarity. Okay, so actually the exact definition of cosine similarity is cosine theta. Theta is the angle between two vectors. Okay, so exact definition of cosine similarity is cosine theta, where theta is the angle between these two vectors. Okay, so that's exact definition of cosine similarity, like this. Okay, so if you look carefully here, so if this angle is very small, okay, if this angle is very small, then the cosine similarity is close to 1, right? So similarity is almost 1. And this angle is very big, like a 90 degree or something, okay, then this angle is 90 degree, okay, then this cosine value is 0, okay, so then means similarity is 0, okay. So so the bigger the angle is, the less similar the data are, okay. So that's the definition of cosine similarity, okay. So in cosine similarity, the direction of data is more important than distance itself. So we use a different geometric interpretation of data. Okay, so data is represented as vector, and what matter is the angle between them. Okay, and the cosine of the angle is the exact definition of cosine similarity. Okay. So as you can see here, a vector has magnitude and direction, okay? So actually what matter is its direction. So cosine similarity actually is a measure that calculates the cosine of the angle between them. As I said, that's the definition of the cosine similarity. It's the cosine of angle between two vectors, two data, okay? So cosine similarity is very popular, especially in text processing. When you represent text, many people use cosine similarity to measure the similarity between two documents. Okay, you can use this cosine similarity in many other applications, but this text processing is a typical example of using cosine similarity. And finally, this is the formal definition of cosine similarity. Okay, cosine similarity is cosine theta. Theta is the angle between two vectors, and the formal definition is given as follows. Okay, so that was cosine similarity. One of the issues of IBL algorithm is how many nearest neighbor you're gonna choose. Okay, uh, so that's the topic of this slide, how to choose k. K is the number of neighbor. So if large K means you choose many nearest neighbor. So in that case, your algorithm, your IBL algorithm is less sensitive to noise. Okay, so because there are many nearest neighbors, maybe a few of them is error, is noise, but your algorithm is robust enough, okay, to handle that. Okay, so algorithm is less sensitive to noise. And if you wanna estimate the probability distribution of class values, then this large K gives you a better estimate of it. Okay. And if you wanna choose large K, then you definitely need larger training data. Okay. On the other hand, small k, that means you choose just a few neighbors, right? Then it's opposite, okay? It's sensitive to noise. So if your data has a lot of noise, you know, just small k is not a good idea, okay? Your algorithm is sensitive to noise. But this small k actually captures the fine structure of problem space better. So if you're interested in the exact shape of problem space, then this small k actually gives more clear idea of the fine shape of your problem space. Okay, that's the advantage of small k. And if your training data is small, definitely you need to choose small number of neighbors. Okay. So balance must be struck between large K and small k. But in many IBL, it's somewhere between like between 7, 9, or 11, 13 something. Okay. This shows the strengths of IBL. The first reason is uh, when you run IBL, the results are readily understandable. That means it's okay. You run IBL and you get the result. Okay, then the IBL actually gives you the reason why this IBL algorithm arrives at this particular result. Okay, it can explain the reason. It goes like this. This new data is very similar to this data. Okay, so because of that, you know why you have this particular result. Okay. And the second strength is you can apply IBL to any arbitrary data types. So you can apply this IBL to numeric data, numeric attribute, or categorical attribute, or any other attribute type. Okay, so that's another advantage. And also you can apply this IBL to other data types like image or text or audio as well. And the third one is it works on almost any number of attribute. So as far as the number of attribute is concerned, there is no limit. Okay. So as we know, the performance of IBL actually depends on the size of training data. So IBL algorithm stores entire training data set, right? So because of that, the performance of IBL depends on the size of training data. But as as for the size of attribute, as for the number of attribute, actually there is no limitations, right? So that's the advantage of this. Another advantage of strengths of IVL. Okay. This shows the weakness of IVL, and the first one is it is computationally intensive during prediction phase. So in IVL, in a training phase, actually it does nothing. It simply read training data, just store them. Okay, so it virtually does nothing in a training phase. So the penalty for IVL occurs during a prediction phase, okay, not the training phase. But in the prediction phase, then what it does here in IVL is it finds the nearest neighbors, okay, by applying the distance function to all the attribute of all the record in the training data, okay. So you have now you have a new data in prediction phase, then you go to the training data set, and for every attribute of every record there, you apply distance function. Okay, so that's why this is very computationally intensive. Its computational complexity is very high. Okay, so that's the first weakness of IVL. Second one is in IVL it stores entire training data. So because of that, you need large amount of storage for training set. Okay, that's second weakness of IVL. And the third weakness of IVL is it heavily depends on distance function and combination function. Okay. So depending on your application, you should choose a proper distance function and the combinations function. Okay. So it depends on particular choice of distance function and combination function. And also it also depends on the number of neighbors k as well.